All right, welcome to the Explainer. Today, we're diving right into the invisible forces that literally shape our universe. We are locking in strictly on the core mechanics of magnetic fields, specifically following the Cambridge A-level physics syllabus. Let's get into it. So, you might be wondering, how exactly do moving charges manipulate the invisible fabric of space? It's a massive, fascinating question, right? Well, to answer it, we're going to drill down from the macroscopic push of magnetic forces all the way down into the nitty-gritty subatomic behavior of the charges themselves. Here's the roadmap for today. We're breaking this down into 5 logical building blocks. First, the concept of magnetic fields. Second, forces on current-carrying conductors. Then, forces on moving charges, magnetic fields from currents, and finally, mastering electromagnetic induction. Okay, Section 1, Concept of Magnetic Fields, the invisible defined. Right off the bat, a magnetic field is fundamentally a field of force, and it's produced by either moving charges or permanent magnets. We have to remember these aren't just magic invisible halos around your fridge magnets. They are actual physical forces, and they are generated by the movement of electrical charge itself. Moving on to Section 2, Forces on Current-Carrying Conductors, the push. So, we know charges create fields, but what happens when we place a wire full of those moving charges directly into an existing magnetic field? Well, an actual physical force acts on that conductor. The invisible field interacts with the moving charges zooming through the wire, and it results in a literal, tangible push. To actually calculate that push, we rely on a completely crucial equation, F equals BIL sine theta. But, let's translate this math into the real physical world for a second. Okay, so that physical force, F, grows stronger if the magnetic flux density, B, is cranked up. It also increases if you bump up the current, I, or if you simply lengthen the wire inside the field, L. And because of that sine theta component, this is key, the force hits its absolute maximum when the wire sits at a perfect 90-degree angle to the magnetic field. Pretty cool, right? And that brings us to a really foundational definition. Magnetic flux density is explicitly defined as the force acting per unit current, per unit length, on a wire placed at right angles to the field. You absolutely need to memorize this, because it pins down exactly what B means in practical terms. Now, to interpret the physical direction of that sudden force, we rely on the legendary Fleming's left-hand rule. Literally, just by aligning your thumb, first finger, and second finger at right angles, you can reliably link the directions of the current, the field, and the resulting physical force. It's like a built-in cheat code for physics. All right, Section 3, Forces on Moving Charges, the micro drill down. Let's zoom way in here past the macroscopic copper wire to see how the field manipulates an individual free-moving charged particle. For this, we use a neat variation of our previous formula, F equals BQV sine theta. This lets us calculate the force on a single, solitary moving charge rather than the whole wire. Breaking this one down, the force on our tiny particle really intensifies if the charge itself, Q, is larger, or if its velocity, v, is faster. And exactly like before, the angle dictates everything. You get maximum force at 90 degrees and absolutely zero force if the particle is just traveling parallel to the field lines. Now, this microscopic deflection, it has some absolutely brilliant real-world applications. It pushes charges to one side of a conductor, and that creates a measurable potential difference, which we call the Hall voltage. We can harness this using a Hall probe to measure magnetic flux density, or even better, use crossed electric and magnetic fields to precisely select the velocity of specific particles. It's a real game changer. Moving on to Section 4, Magnetic Fields from Currents, Creating the Invisible. So, if fields push currents, it's time to flip the script. Let's explore how currents actually generate these fields in the first place. The shape of the wire drastically changes the shape of the field. A long straight wire, that creates simple concentric circles radiating outward. But if you loop that wire into a flat coil or a long solenoid, you combine those fields, literally concentrating the invisible lines into a powerful directional beam right through the center. And here's the best part, we can artificially amplify that beam so easily. Just by sliding a ferrous core directly into the solenoid center, you radically increase the magnetic field. This exact same principle of overlapping magnetic fields is also what causes adjacent current-carrying wires to physically attract or repel one another. Okay, final section. Section 5, Mastering Electromagnetic Induction, Harvesting the Power. For our final conceptual leap today, we're looking at how to harvest this relationship between motion and magnetism. But before we generate any power, we have to define magnetic flux, represented by the Greek letter phi. It's the product of the magnetic flux density and the cross-sectional area. Think of it kind of like catching rain in a bucket. It's the total amount of magnetic field passing through a specific area, and that becomes magnetic flux linkage when you multiply it across a coil with multiple turns. So, there are 3 chronological mechanics to induction. First, a changing magnetic flux induces an electromotive force, or EMF. Second, this induced EMF naturally opposes the change that created it. And third, specific factors like the speed of the changing flux directly affect the magnitude of that EMF. Basically, moving a magnet near a wire quite literally forces electricity to flow. It's amazing. We can summarize those steps with 2 completely foundational laws. Faraday's law quantifies the magnitude of the induced EMF, and Lenz's law dictates the direction, stating it always opposes the change. These 2 principles right here, they are the absolute governing rules behind almost all global electricity generation. So marrying the formulas for magnetic flux with the laws of Faraday and Lenz, that's the ultimate goal here. It's this beautiful intersection where motion, magnetism, and electricity all become completely interchangeable. Which brings us to a seriously mind-bending conclusion. If moving charges create fields that in turn move other charges, where does the cycle truly begin? I'm going to leave you with that final paradox to ponder, thinking about the invisible forces that literally bind our physical universe together. Keep studying, keep questioning, and I'll catch you in the next explainer.